Okay, continuing the study of integration where we are estimating the area under the curve. So this is an example where a curve is given, our function is given, and rectangles are drawn. We can see heights, we can see widths, and we're simply just going to find the area of each of these individual rectangles. Okay, so we don't have actual height values, but we have the x-coordinate for where the height occurs. So we need to take that x, evaluate it in the function to come up with the corresponding height. So we need to know what is f of 4/10, what is f of 1.2, and what is f of 2. This is certainly just a calculator question. You wouldn't be expected to know sine of 0.4. So if I put this in the calculator, I would get 11.07, 14.4, and 10.9. So those are the heights of the corresponding rectangles. If I look at the width of each one, I have a width of 1, I have a width of 0.8, and I have a width of 1.1. So if I multiply the heights by the widths, and I add them up, I would arrive at an answer of 34.58 units squared as the approximated area. All right, so this section is going to get heavy in the notation, just to start to get comfortable with how do we notate this idea of integration. So what would happen if we continue to increase the number of rectangles that we use to find the area under the curve, right? If the delta x approaches 0, would the approximation get better or worse? So if the delta x approaches 0, the n, the number of rectangles, in turn approaches infinity, are we doing a better job or a worse job? So it would definitely be better because we would use more actual function values as our heights and fewer approximations. So if the number of subintervals increases without bound, n approaches infinity, then the length of each subinterval approaches 0. This limit of a Riemann sum is used to define the definite integral. If f of x is defined on a closed interval from a to b, then the definite integral of f of x from a to b is defined as, so here's our integral symbol of f of x, so the integral from a to b of f of x dx. So I always explain the dx has to be there. That's implying that I'm integrating a function that was previously derived with respect to x. We essentially are looking at derivatives. We are finding the area under a derivative curve, and this integration process is bringing us back to our original. So in that first example in 5.1, we were looking at the area under a velocity curve or a speed curve, and that told us how far did we travel. It brought us back to a position function. The Riemann sum, the limit as n approaches infinity from 1 to n of f of xi, delta x. So that's what the AP students investigated in 5.1. So this idea of integration, of course, is exactly equal to those Riemann sums. Okay, this means the definite integral represents the area under the curve. So just like in chapter 3 when the derivative was defined as the slope of the tangent line, the integral is defined as the under the curve. So signed area matters, of course. If we're looking at the area above the x-axis versus the area below the x-axis, we have positive versus negative. So oftentimes we take a look at what's considered the net area. Right? Sometimes the net area is 0. The positives and the negatives cancel out. Similar to a velocity type question where you travel north and then you travel south. Well, positive and the negative, it makes it look like you traveled 0. The integration from a to b is the signed area of the region between the graph of f of the graph and x and the x-axis. So all integrals is always the area for now between the x-axis and the curve. Okay? We can integrate with respect to y, and then it would be the space between the function or the equation and the y-axis. All right, so here's our first example. We still don't know how to truly integrate, so we're going to still use geometry. We're going to use graphs and geometry. So I'm going to graph the function inside of the integral from 0 to 5, which means I need to know a little bit about my function. My function is 3 minus x. Slope of -1, y-intercept of 3, x-intercept of 3. and we are stopping at 5. So we have a triangle above and a triangle below that we can calculate the base and the height for. So we have 1/2 base height, positive area, 1/2 base height, negative area. You can also think of it as 1/2 base height minus 1/2 base height, however you would like to think about it. So we have 1/2 times 3 would be the base of the first triangle, times another 3 would be the height of the first triangle. The base of the second triangle, 3 to 5, is just 2. The height of the second triangle, if I evaluated 3 minus 5, I would get 2 as well. I would get -2. So it's up to you if you want to put the height in as the negative or use the subtraction. It doesn't make a difference. Either way, the answer is 2.5, the difference between the positive and the negative area. Now, what happens if I try to integrate the absolute value of 3 minus x? Right? Very similar graph, except that absolute value symbol at the x-intercept of 3 reflects the graph back up. Right? So that negative triangle is no longer below the x-axis, it is above. We'll be investigating a lot of absolute value functions with integration. The key is figure out where the x-intercept is and reflect the negative portion of the graph positive. We'll keep looking at these as we move through this chapter. So now I don't have any negative area. I have a 1/2 3 times 3 plus a 1/2 2 times 2. So I end up having 13 over 2 for my area. I want you to try all 3 of these on your own. Sketch the function, find the area between, right? Use geometry, and we'll talk about these in class. Here's some properties. So before we actually learn the process to integrate, there's a couple of things that you're allowed to do. You're allowed to say that, well, if I just have a constant, right, based on the previous problem that you just explored, if I just have a constant, well, that constant's always going to be a horizontal line, and therefore when I divide it into some interval from a to b, I'm creating a rectangle. So any integral of a constant becomes c times b minus a. The second one says if you're integrating a sum, you can distribute essentially the integral to each term through addition. And if you have a coefficient, you can pull that out in front. So that helps us with something like this. We are clearly told that the integral of f of x from 0 to 5 equals 5, and the integral of g of x equals 12. We don't know anything else about the integration process here. So before I can apply these, I need to isolate or expand the integral at the bottom. So I can do so by distributing through the subtraction. So I first have the integral from 0 to 5 of 2 f of x, apply the dx to each, minus the integral of 1/3 g of x dx. Then I can bump these coefficients out in front. So I have 2 times the integral from 0 to 5 of f of x dx minus 1/3 times the integral from 0 to 5 of g of x dx. So I know that the first integral equals 5, the second integral equals 12. So I have 2 times 5 minus 1/3 times 12. 10 minus 4, or 6. Another important theorem or definition in this section is reversing the limits. We'll use this a lot. Notice the first way it's written, it goes from B to A. The second way it's written, it goes from A to B, but there's a negative sign. So we can change direction. It's kind of like going from left to right across the graph would be a positive direction. Right to left across the graph would be a negative direction. So when we need to change the limits of integration, we can do so by negating that integral. Okay. We also have this theorem called additivity for adjacent integrals. That means that if I have some function, right, it has to be the same function, and they have to be adjacent. If I have some function, whatever, some curve up here called f of x, and we have a, we have b, we have c, right? If I'm finding the area under the curve from a to b, and I'm finding the area under the curve from b to c, the sum of them is, of course, the total area under the curve. So I can either use it to work in the direction of putting them together, or I can break up into individual integrals when that's necessary. So here's an example for how that can help us. If we want to rewrite each of these as a single integral, so I can acknowledge that I have from 2 to 9 the integral of f of x dx, and I'm subtracting the integral from 4 to 9 of f of x dx. So I want to see what's left. What do I want to actually find the area of? Drawing can help, but you don't have to, right? So I have 2 to 9, that's the whole space, and I'm taking away 4 to 9. So what am I left with? I'm left with the space from 2 to 4. Okay. The second one requires both. Notice that the first integral goes from 7 to 3. We don't really like it written that way. You want to make sure most of the time that you're written with the smaller number being the lower limit. So you are working from left to right across the graph. And when I flip them, I needed that negative sign out in front. So now I have negative integral from 3 to 7 f of x dx plus from 3 to 9 f of x dx. So quick sketch. I'm going to start with the larger one, so 3 until 9, that's that whole space, and I'm subtracting out 3 to 7, which means I'm left with 7 to 9. So lots of important theorems in here, but big picture, we found exact areas under curves in this section. We use geometry in order to do so. So understanding the notation of the integral, some of its properties and theorems, and then moving forward, we're going to look into the actual integration process. How do we anti-derive or undo a derivative is what an integral is doing.